Good morning, students. My name is CH.S.V.PRASAD Rao, and I am working as senior lecturer in electrical department at Government Polytechnic, Yadgirigutta. Today we will handle this AC motors subject. In this, we have the fourth chapter, characteristics of three-phase induction motor. In this chapter, in the last class, we have covered condition for torque under running condition of induction motor and torque slip curve. So, when we are we have derived the torque equations, that is for full load torque and starting torque, and next maximum torque. We have derived condition for maximum torque also. So the torque is maximum when armature resistance is equal to synchronous reactance. So that is the condition we have derived. How we derived? We have taken the full load torque equation and we have differentiated the torque equation with respect to variable, that is slip, when and equal to 0. When we differentiate the torque equation with respect to variable, that is slip s, and equal to 0, then we got a condition that resistance is equal to rotor resistance is when the torque is measured, when the rotor resistance is equal to reactance under running condition, that is R2 is equal to SX2. So S is equal to R2 by X2. If we substitute in the torque equation, then we can get the Mason torque value. And we have derived the relations also, that is starting torque and Mason torque. So the relation between starting torque and Mason torque, TST by Tmax is equal to 2a by 1 plus a square, and similarly T full load by T maximum load is equal to 2as by a square plus s square. So on this we have derived the relations, and we have draw the curve also. Torque can on slip on x-axis and torque on y-axis. Then we can get torque slip curve. So from this we have observed the point when speed is synchronous speed, that is ns is equal to nr, then slip is equal to 0, torque is equal to 0. So when the load is increases slowly, the speed decreases and slip increases. Then slip will be very small. So then T is proportional, so yes, for low values of slip, the torque slip curve represents a straight line. So next, as load increases, slip decreases, speed decreases, and slip increases, and torque increases. Torque increases and reaches to its maximum value when slip S is equal R2 by X2. This is the maximum torque, which is also known as pull-out torque or breakdown torque. So why it is called breakdown torque means if we further increase the speed slip beyond Tmax, then the torque decreases and the slip increases for high value of slip. Hence, the torque slip curve represents a rectangular hyperbola. Starting torque depends on the rotor. Should be more than the torque required by the load connected to the motor shaft to enable the motor to start with the load. The magnitude of the starting torque and maximum torque depends upon the rotor resistance. The effect of various rotor resistance on the torque slip curve of an induction motor also we have noted. That means if resistance changes, automatically the torque value changes, and if we draw the curve on that one, that gives the torque slip curve. So now we will solve the problems on the torque. So he given a problem. Note down the problem. He given a problem. A 6-pole, 50 hertz, 3-phase induction motor has rotor resistance and standstill reactance of 0.03 ohms and 0.1 ohm per phase respectively. Calculate the value of the external resistance to be connected in the rotor circuit to obtain 80% of the maximum torque at starting. So what is the given data? He given P is equal to number of poles, P is equal to 6, frequency is equal to 50, and rotor resistance R2 is equal to 0.03 and standstill reactance, so that is X2 0.1 ohm per phase. Calculate the value of external resistance. So that means how much amount of external resistance we have to connect in series with the rotor circuit to obtain 80% of the maximum torque at starting. So this is the condition. First we will write the given data. So number of poles P is equal to 6 and frequency F is equal to 50 Hz. Rotor resistance R2 is equal to 0.03 ohms per phase and standstill reactance, rotor reactance X2 is equal to zero point 0.1 ohm per phase, and given starting torque is equal to 80% of the maximum torque, that is TST by Tmax is equal to zero point 0.8. So we have formula, the relation between starting torque and maximum torque is equal to 2a by a square plus 1. So that is ratio of starting to maximum torque, that is 2a by a square 1 plus a square. So that is equal to zero point 0.8. So here we have to do the cross multiplication. Then we will get quadratic equation. Note down this. So that is 1 plus a square is equal to 2a by 0 0.8. So if you do the cross multiplication, we can get a quadratic equation a square minus 2.5 a plus 1 is equal to 0. So there is one variable and one equation. If you solve this equation, we can get a value as, here we have to use the formula minus b minus a plus or minus square root of b square minus 4ac by 2a. So that is a is equal to minus of minus 2.5 plus or minus square root of minus 2.5 square minus 4ab, 4 into 1 into 1 divided by 2a. So that is 2 into a is 1. So we get a value a is equal to 2 or 0.5. This is the slip value. So small value of a must be considered. So 2 is value 2 is neglected and we have to take 0.5. So that is we taken 0.5. Note down this. Note down the steps. So this is just a simple problem. Just we have to substitute the values in the mathematical equation. So let us assume a external distance of r is added. Then R2 plus R will be the total resistance. Then the ratio of rotor circuit standstill resistance, that is R2 plus R by x2 is equal to 0.5, where x2 value is 0.1 and R2 value is 0.03. Then it is one equation, one variable. We have to do cross multiplication, that is 0.1 into 0.5, and next reduce 0.03 like this. R is equal to 0.5 into 0.1 minus 0.03. That gives external resistance to be added in series is 0.02. Note down this. So we have to add a external resistance of 0.02 in series with the rotor circuit, so that 0.02. Note down this. So over. Any doubt in this one? If you have any doubt, you practice this and ask me in the next class. So next problem is a 4-pole 50 Hz 7.46 kilowatts motor has at a rated voltage and frequency a starting torque of 120 percentage and maximum torque of 20% of full load torque. So determine full load slip and slip at a maximum torque. So in this problem, he given number of poles P is equal to 4 and F is equal to 50 and rating of the motor, that is 7.46 kilowatts, and voltage is has a rated voltage and frequency, and its starting torque is 160 percentage and a maximum torque of 200 percentage of full load torque. Determine first bit full load speed and speed at maximum torque. So if you write the given data, P is equal to 4, F is equal frequency, F is equal 50, output is equal to 7.46 kilowatts, starting torque TST is equal to 160 into T, that is full load torque. Similarly, maximum torque Tm is equal to 200 percentage of full load torque. Determined full load speed at maximum torque. So given data, number of poles P is equal to 4, frequency 50 Hz, and TST is equal to 60 percentage of full load torque, and maximum torque is equal to 200 percentage of full load torque. So TST by TFL is equal to 1.6 The ratio of starting torque to the full load torque 1.6 and T maximum by 2 full load torque is 2. So it is given 200 percentage. So that is 2. So T starting by T max is equal to 1.6 by 2. This is equation 1 and this is equation 2. So 1 by 2. So that is T starting by T maximum is equal to 0.8, 1.6 by 2. So that is T starting by T. But we have relation between T starting by T max. What is that? Anyone can guess? The relation between starting torque and maximum torque is equal to 2a by a square plus 1. To this point A, you have to equate to that equation. That is 2a by a square plus 1. So this is T starting by T maximum and equate to that is 2a by 1 plus a square. If you do the cross multiplication of this one, then we can get a one quadratic equation and one variable, that is 0.8 a square plus 2a plus 0.8 is equal to 0. From this we can get a values has two values we can get. So one value is a is equal to 0.04. This is the lowest value, and another value is high value, that is neglected. So we can take a is equal to 0.04. So next he given a relation T full load by T max is equal to 2as by a square plus s square, that is equal to 1 by 2. So substitute a value is already there 0.04 and one equation and one variable. If you solve this, we can get s value. So what is the s value? That is slip is equal to 0.01. Note down the steps. Copy the steps fastly. This is only a formula substitution. Only a formula substitution. We calculate the slip. So synchronous speed ns is equal to 120 f by p. So that is 1500 rpm. So rotor speed, full load speed nr is equal to ns into 1 minus s. So that is 1500 into 1 minus 0.01. So that is 1485 rpm. So that is the full load speed. Slip next, slip at maximum torque. So that is we have calculated the slip a value, that is 0.04. So this is the slip at maximum torque. So speed at maximum torque is equal to nr is equal to ns into 1 minus s. So that is 1500 into 1 minus 0.04, that is 1440 RPM. Note down this. This is only a formula substitution. We must be thorough with the relations and the formulas. So we have calculated full load speed and speed at mass and torque. అలాగే సార్ 3 horse కదా. So this is we have calculated the both two. So both we have calculated. See, speed at full load speed and speed at mass and torque. Next, advantages of three-phase induction motor. So what is the advantage of three-phase induction motor? So one is it is simple in construction, extremely rugged, and almost unbreakable construction, especially squirrel cage type. Squirrel cage type, and it has a low cost and low cost and highly reliable. Highly reliable. And next, it has sufficiently high efficiency. High efficiency. So this is the importance of three-phase induction motor. And another one is it and another one is it is has self-starting also. That is also a property of three-phase induction motor. So these are the advantages of three-phase induction motor. So if you see the construction, a synchronous motor essentially consists of two parts. So that is stator and rotor. The stationary part is called stator and the rotating part is called rotor. So the stator contains a cylindrical steel having laminations on the inner periphery. On that we will place the stator winding. So that is according to our requirement. Either we connect and the number of poles that depends on the speed. So if the what is the requirement of the speed? So depending on that, we will design the number of poles, and the winding terminals are brought out and they are connected to terminal box. From terminal box, we can connect to supply. Connect to the supply. So when we connect the supply to a three-phase stator winding, then it produces a rotating magnetic field of constant magnitude, that is 1.5 times the maximum flux, and rotating at synchronous speed is produced. Rotating at synchronous speed is produced. So the resultant flux is of constant magnitude, that is 1.5 times the maximum flux at any flux. So if you see rotor, the rotor is a rotating part. There are two types of rotors, that is slip ring induction motor, squirrel cage induction motor, and phase wound rotor. So which rotor we will use for a induction motor, depending on that we will call the motor. Suppose if you are using squirrel cage rotor, then we can call it a three phase squirrel cage induction motor. If you are using phase wound rotor, then we can call it as three phase wound rotor. So if you see the squirrel cage rotor, almost 90% of induction motors are squirrel cage type, because this type of rotor has the simplest and most rugged construction and is almost strong as compared to other motors. The rotor core is a laminated steel cylinder having slots on outer periphery. A common practice in constructing the swirl cage is to place the assembled core in a mold and then force the molten conducting material, aluminum or copper, in the slots. The rotor conductors need not be insulated from the core, since the current flow through the least resistance path of the conductor. The rotor bars are short-circuited at both ends by using end rings. And another thing is, the rotor slots are not made parallel to the rotor shaft axis. They are skewed at a certain angle to reduce magnetic noise during working. That is one point. Another point is to produce a uniform torque. That is second point. Next point is to prevent possible magnetic locking called cogging of the rotor with stator. So that's why the rotor shaft is the rotor axis is not made parallel to the shaft. They are skewed at a certain angle. In some cases, the heavy conductor bars are driven into the slots. The end rings with holes are provided too for cooling purpose. So this is the construction of squirrel cage rotor. Next one is phase wound rotor. It consists of laminated cylinder cylindrical core having slots on the outer periphery and is provided with a three-phase distributed winding in the insulated rotor slots similar to stator winding. The rotor is wound for as many number of poles as the stator poles and is always connected for a three-phase. Even the stator is wound for two-phase. So in this case, phase wound rotor, the three phases are started starred internally and the other three windings are brought out and connected to three insulated slip rings mounted on the same shaft with brushes rested on them. So these brushes are connected to three-phase star-connected rheostat. This arrangement makes it possible to add external resistance to each phase of the rotor circuit during starting period for increasing starting torque and as well as to limit the starting current. So this external resistance will be there in the rotor circuit only at the time of starting. Under normal running condition, the slip rings are automatically short circuited by means of metal collar which is pushed along the shaft and connects all the slip rings together. Then the rotor is short circuited itself and works as squirrel cage rotor and the brushes are lifted automatically to reduce friction, wear and tear. So this is the construction of stator and rotor. So when we give a supply to a three-phase three-phase stator winding, then resultant flux is produced whose magnitude is equal to 1.5 times the maximum value of the flux due to any phase in a three-phase supply. The resultant flux rotates around the stator at a synchronous speed. So that is Ns is equal to 120 F by P. where F is equal frequency, P is equal number of poles. So for working of three-phase induction motor, a three-phase revolving flux of constant magnitude and synchronous speed is required. This can be obtained by means of three-phase supply given to stator conductors. So further, the rotor is set up by using Faraday's laws of electromagnetic induction and Fleming's law and Lenz's law. So T starting is equal K2 into R2 square plus S2 square, where K is the constant. So T starting is equal K2 into R2 by R2 square plus X2 square. Differentiate the torque, starting torque and equate to 0. So we can get the maximum torque when R2 is equal to X2. So starting torque is maximum value. Substitute this value, that is K into E2 square by 2x2. This is the maximum torque value at the time of starting. So from this equation you can see the maximum torque is independent of rotor resistance and it is inversely proportional to rotor reactance. If you substitute the K value, that is 3 by 2 pi ns, then you can get T maximum like this. So this is the relation between maximum torque and normal torque. So gross torque Tg is equal to P2 by 2 pi ns. So torque in synchronous watts is equal to rotor input, rotor copper losses by S, or gross rotor power output Pm by 1 minus S. It is seen that the mass and torque does not depend on R2 and exact location of Rt max is independent on this. So that means there is no relation between mass and torque and resistance. Greater the R2, greater is the value of slip at which mass and torque occurs. So T is proportional to S.V. square. So in general, operating torque at any slip is equal to at any slip by mass and torque is equal to 2as by a square plus s square. This thing we have derived. So that is the next, the relation between T starting by T max is equal to a by a square 1 plus a square. So this is the torque slip curve for different values of resistance. So this is for a resistance R, this is 4R, this is 6R. So that is at where the torque value is maximum is same. See here, it is not changing with the rotor resistance, but the slip where it is occurs is changing. So why? Because slip at mass and torque is equal to R2 by X2. So if resistance changes, mass and torque is same, but the slip where it mass and torque is occurred changes. Here it is occurs at 0.2. Here it is occurs 0.3. Here it is occurring at 0.5. So it shows the maximum torque value is independent of rotor resistance, but only the location where the slip is maximum will be changes. So this is the torque values. Gross torque is equal to P2 by 2 pi ns by 60, or this is the rotor input by 2 pi ns by 60, or gross power by 2 pi n by 60, where shaft torque is equal to P output by 2 pi n by 60. So rotor gross output is equal to rotor input into 1 minus s. So our Pm by P2 is equal to 1 minus 1 minus s, that is equal to rotor speed by synchronous speed. So from this we can noted the points. The slope of the straight line depends mainly on the rotor resistance. Higher the resistance, sharper the slope. The linear relation between torque and speed is shown here. So it is torque T1 occurs at a speed n1, torque T2 occurs at a speed n2. So this is the maximum torque is called breakdown torque. This is the torque relation. If it goes below the synchronous speed, that is negative value, then it works as a generator. So synchronous works is by defining a new unit of torque instead of force at radius. We can say that torque is equal to rotor input. The new units is synchronous watts. So what we have covered, we have calculated the speed at maximum torque, next maximum torque, and full load torque. So frequently what they will ask these questions. Define synchronous parts. This is for 2 marks or 3 marks. Next, explain the torque versus speed characteristics of induction motor under load. This is for 5 marks or big question he will give. So take the assignment as these two questions problems, as we done the same type of problems. These two are a 3-phase 400 by 200 volts star connected wound induction motor has here point not hyphen 0.06. This is not hyphen, this is point 0.06 ohms rotor resistance and 0.3 ohms standstill reactance per phase. Find the additional resistance required in the rotor circuit to make the starting torque equal to maximum torque of the motor. Next problem. A 746 kilowatts 3 phase 50 Hz 16 pole induction motor has a has a has a rotor impedance of 0.02 plus, this is not hyphen, this is 0.02 plus j 0.15. 0.02 is the resistance, 0.15 is the reactance at standstill. Full load torque is obtained at 360 rpm. Calculate first bit. the ratio of full load torque. Next bit, the speed of maximum torque. Next bit, the rotor resistance to be added to get maximum torque. So do these two problems. If you have any doubt, I will explain in the next class. Thank you.